Hello Matrix. Let's dive into the groundbreaking work that was published back in 2014 by Kyunghyun Cho and his team at the University of Montreal. This work fundamentally shifted how we approach machine translation and many other sequence transduction tasks in natural language processing. The paper presented a novel neural network architecture, known as the Recurrent Neural Network, RNN Encoder-Decoder, which was designed to capture phrase representations in the context of statistical machine translation. In the realm of machine translation, we're dealing with the challenge of translating sentences from a source language to a target language. Traditionally, this task was approached with statistical methods that relied heavily on handcrafted features and complex algorithms. The introduction of the RNN Encoder-Decoder marked a significant departure from these methods, offering a more streamlined, end-to-end approach. So, what's the secret sauce here? The RNN Encoder-Decoder consists of two main components, you guessed it, an encoder and a decoder. Both the encoder and decoder are recurrent neural networks, a type of neural network that's designed to process sequential data. The encoder's job is to process the input sentence, one word at a time, and to create a fixed-length vector representation that captures the semantic essence of the input sentence. This vector is often referred to as the context vector, as it encapsulates the context of the entire input sentence. Once the encoder has processed the entire input sentence, the context vector is passed on to the decoder. The decoder, another RNN, then generates the translated sentence, one word at a time, using the context vector as its guide. In essence, the decoder is translating the context of the source sentence into the target language. The magic of this architecture lies in its ability to handle sentences of varying lengths and to capture the dependencies between words that are far apart, thanks to the recurrent nature of the RNN. Furthermore, the whole system is trained end-to-end, meaning that we don't have to worry about designing intricate features or rules. The paper showed that this architecture could learn to translate short English sentences into French with surprising accuracy, outperforming more traditional phrase-based translation systems on some tasks. The RNN encoder-decoder model laid the foundation for the development of more complex architectures, like the sequence-to-sequence model and the transformer, which have since dominated the field of machine translation. Continuing our journey, the RNN encoder-decoder model isn't just a paradigm shift in machine translation, but it also introduced a new way of thinking about neural networks and sequence processing. The power of the RNN encoder-decoder stems from its ability to generate a fixed-length vector representation of a sentence, irrespective of its length. This was a game-changer. Before this, creating a meaningful representation of variable-length sentences was a significant challenge. The model's encoder-decoder structure provided a blueprint for many subsequent models in natural language processing and beyond. Today, encoder-decoder architectures are commonplace in tasks, ranging from text summarization to image captioning. Another key innovation presented in the paper is the use of a specific type of RNN known as the long short-term memory (LSTM) network in the encoder and decoder. LSTMs are designed to mitigate the vanishing gradient problem, a common issue in training regular RNN, where the contribution of information decays geometrically over time, making it difficult for the model to learn long-range dependencies. LSTMs handle this by using a series of gating mechanisms that control the flow of information, allowing the model to remember or forget information as needed. This makes them particularly suitable for tasks like machine translation, where understanding the context and maintaining the continuity of information is crucial. However, the model also had its limitations. As the paper pointed out, while the RNN encoder-decoder could handle short sentences reasonably well, its performance significantly degraded with longer sentences. This was primarily because of the model's reliance on a single fixed-length vector to capture the entirety of the input sentence's context. This is akin to trying to cram the entire plot of a long novel into a single paragraph. Inevitably, some details are going to get lost. This shortcoming led to further innovations, such as the introduction of attention mechanisms, which allowed models to dynamically focus on different parts of the input sentence during the translation process, thereby significantly improving the handling of longer sentences. But that's a story for another day. For now, let's appreciate the revolution brought about by the RNN Encoder-Decoder model. It's a pivotal piece in the puzzle of how we've got to where we are today in the field of neural machine translation and many other areas of artificial intelligence. If you found this discussion helpful, let us know in the comments, and don't forget to hit the subscribe button. We have many other videos that cover a wide variety of topics on science and artificial intelligence.